Who's reporting?
Morel, Helen, Ira, Cheska, Srija, Crystal, Ryoko Kazumi.
Presenting the continental drift theory.
Good day, everyone. Praise be Jesus and Mary. Hi, I am Marl B.
I am Mary Helen Rose Cheadle Watton.
I am Cheska May Cabanyero.
I'm Ira C.
I am Trisha May G. Normore.
I am Ryoka Kazumi Figueroa.
And I am Crystal Opaber.
And we are the presenters of Group 3. So, our topic for today's video is all about the continental drift theory. Before we start our discussion, let me just ask a few questions about the continents. Do you have an idea about the continents of the Earth? What are the 7 continents upon the Earth? What is the largest continent among the 7 continents? At the end of this topic, we should be able to describe Wegener's theory of continental drift, explain the main evidences that support Wegener's theory. The lesson outline: what is continental drift theory? Who formulated the theory? And what are the 4 main evidences of continental drift theory? So, what really is a continental drift? Continental drift is the hypothesis that the Earth's continents have moved over geologic time relative to each other, thus appearing to have drifted across the ocean bed. The idea of continental drift has been subsumed into the sources of plate tectonics, which studies the movement of the continents as they ride on plates of the Earth's lithosphere. Continental drift describes one of the earliest ways geologists thought continents moved over time. This map displays an early supercontinent, Gondwana, which eventually moved to form the continents we know today. Fossils of similar organisms across widely disparate continents encourage the revolutionary theory of continental drift. 600 million years ago, a supercontinent known as Rhodina split apart, and a vast ocean filled the basin. Colliding tectonic plates created mountain ranges, and a shift in global climate allowed glaciers to spread as far as the equator. A new supercontinent named Pannotia formed in the South Polar region.
Pannotia, from Greek pan, means all, notos, south meaning all southern land, also known as the Venus supercontinent. Greater Gondwana, the Pan-African supercontinent, was a relatively short Neoproterozoic supercontinent that formed at the end of the Precambrian during the Pan-African orogeny, 650 to 500 megaannum during the Cryogenic period, and broke apart 560 megaannum with the opening of the Iapetus Ocean in the late Ediacaran and early Cambrian. So Pannotia formed when Laurentia was located adjacent to the 2 major South American cratons, the Amazonia and Rio de la Plata. The opening of the Iapetus Ocean separated Laurentia from Baltica, Amazonia, and Rio de la Plata. In 2022, the whole concept of Pannotia has been put into question by scientists who argue its existence is not supported by geochronology, or the supposed landmass that began to break up wall before it was fully assembled.
500 million years ago, a chunk of a supercontinent Pannotia drifted north and split into 3 masses, forming Laurentia, which the present day of North America, the Baltica, which the present day of Northern Europe and Siberia. In shallow waters, the first multicellular animals with exoskeletons appeared, and the explosion of life began.
So Laurentia, or the North American craton, is a large continental craton that forms the ancient geological core of North America. Many times in its past, Laurentia has been a separate continent, as it is now in the form of North America, although originally it is also included in the cratonic areas of Greenland and also the northwestern part of Scotland. So during other times in its past, Laurentia has been part of larger continents and supercontinents, and itself consists of many smaller terranes assembled in a network of early Proterozoic organic belts. So small microcontinents and oceanic islands collided with and sutured onto the ever-growing Laurentia, and together formed the stable Precambrian craton seen today. So next is Baltica. So Baltica is a paleocontinent that formed in the Polyproterozoic and now constitutes northwestern Eurasia or Europe north of the Trans-European Suture Zone and west of the Ural Mountains. So the thick core of Baltica, the East European Craton, is more than 3 billion years old and formed part of the Rhydinia supercontinent. And lastly, Siberia. So Siberia, also known as Angaraland or simply Angara and Angarida, is an ancient craton in the heart of Siberia. So today, forming the Central Siberian Plateau, it was an independent continent before the Permian period. The Verkhoyan Sea, a passive continental margin, was fringing the Siberian craton to the east in what is now the East Siberian lowland.
300 million years ago, the landmass Laurentia collided with Baltica. The Appalachian Mountains of eastern North America rose along the edges of the supercontinent Pangaea, and the climate shift thrust the Earth into an ice age.
300 million years ago, Laurentia collided with Baltica. So when two continental plates collide, the crust is bunched up and a mountain range is formed. Continental crust is less dense than oceanic crust. So when two of these slabs of rock collide, neither of them will dive beneath the other, as is the case when continental crust collides with oceanic crust.
200 million years ago, dinosaurs roamed the supercontinent Pangaea, surrounded by the Fantastic Ocean, the oceanic ancestor of the Pacific Ocean.
So where did dinosaurs live? Dinosaurs lived on all of the continents. So at the beginning of the age of dinosaurs, during the Triassic period, or about 230 million years ago, the continents were arranged together as a single supercontinent called Pangaea. So during the 165 million years of dinosaurs' existence, this supercontinent slowly broke apart.
Over 100 million years ago, Pangaea broke apart. The Atlantic Ocean poured in between Africa and the Americas. India broke away from the African continent, and the Antarctica and Australia still connected above the sea level were stranded near the South Pole.
The breakup of Pangaea was principally facilitated by tensional plate stress acting on pre-existing suture zones. The rifting of Pangaea began during the early Permian along the southern Tethys margin and produced the lenticular-shaped continent known as Sumeria.
By 50 million years ago, dinosaurs were extinct from the Earth. Continental fragments collided, pushing up mountain ranges still existing today. The collision of Africa into Europe gave rise to the Alps in Europe, and the collision of India to Asia formed the Himalaya. Birds and animals began to expand in number and diversity.
So the question is, when did dinosaurs become extinct? So dinosaurs went extinct about 50 to 65 million years ago after living on Earth for about 165 million years. If all of the Earth time from the very beginning of the dinosaurs for today were compressed into 365 days, or one calendar year, the dinosaurs appeared January 1 and become extinct the third week of September. About 180 million years ago, the supercontinent Pangaea began to break up. So scientists believe that Pangaea broke apart for the same reasons the plates are moving today. The movement is caused by the convection currents that roll over in the upper zone of the mantle. So these movements in the mantle cause the plates to move slowly across the surface of the Earth. Another question is, what caused the Cretaceous extinction? The exact nature of this catastrophic event is still open to scientific debate. Evidence suggests an asteroid impact was the main culprit. Volcanic eruptions that caused large-scale climate change may also have been involved, together with more gradual changes to Earth's climate that happened over millions of years. Whatever the causes, the huge extinction that ended the age of the dinosaurs left gaps in the ecosystems around the world. So these were subsequently filled by the only dinosaurs to survive, birds and mammals, both of which went on to evolve rapidly. Scientists believe the formation of the Isthmus of the Panama is one of the most important geologic events to happen on Earth in the last 60 million years. So even though it's of land relative to the sizes of the continents, the Isthmus of the Panama had an enormous impact on Earth's climate and its environment. By shutting down the flow of water between the two oceans, the land bridge rerouted currents in both the Atlantic and Pacific Oceans. Atlantic currents were forced northward and eventually settled into a new current pattern that we call the Gulf Stream today. With warm Caribbean waters flowing toward the northeast Atlantic, the climate of northwestern Europe grew warmer. Winters there would be as much as 10 degrees Celsius colder in winter without the transport of heat from the Gulf Stream. The Atlantic, no longer mingling with the Pacific, also grows saltier, so each of these changes help establish the global ocean circulation pattern that we see today. In short, the Isthmus of Panama directly and indirectly influenced ocean and atmospheric circulation patterns, which regulated patterns of rainfall, which in turn sculpted landscapes.
Causes of continental drift. The causes of continental drift are perfectly explained by the plate tectonic theory. The Earth's outer shell is composed of plates that move a little bit every year. Heat coming from the interior of the Earth triggers this movement to occur through convection currents inside the mantle.
So, who formulated the theory? Alfred Wegener in full. Alfred Lothar Wegener, November 1, 1880 to November 1930, is a German meteorologist and geophysicist who formulated the first complete statement of the continental drift hypothesis. Wegener's theory of continental drift was met with skepticism by many scientists. Although he had a lot of evidence to support the theory, he could not explain how the plates move. It would be almost half a century before this problem began to be solved.
So, to understand our world's changing climate, it is imperative that we understand how climates of the past varied. This collection brings together a series of papers published at the scientific data that describe and share valuable data on past climates. Paleoclimate data, the data were obtained from a variety of sources, including historical records that can inform us the recent past, and biological or fossil proxies that allows us to learn about climates that existed long before man walked the earth. They have been organized below into two sections according to the level data processing. Okay.
The first evidence is the apparent fit of the continents. Geological fit evidence is the matching of large-scale geological features on different continents. It has been noted that the coastlines of South America and West Africa seem to match up. However, more particularly the terrains of separate continents conform as well.
But of course, this was just a starting point. Wagner continued his research, and the next thing he delved into involved life. Wagner began to study fossils of ancient creatures and, more importantly, where those fossils were located.
Fossil evidence. Another important piece of evidence in the continental drift theory is the fossil relevance. There are various examples of fossils found on separate continents and in no other regions. This indicates that these continents had to be once joined together because the extensive ocean between these land masses act as a type of barrier for fossil transfer. Four fossil examples include the Mesosaurus, Sagdugnathus, Litroceras, and Glossopteris.
So, fossils provide important evidence for evolution and the adaptation of plants and animals to their environments. Fossil evidence provides a record of how creatures evolve and how this process can be represented by a tree of life, showing that all species are related to each other. It can give us a useful insight into the history of life on Earth. The first fossil example is Mesosaurus. Mesosaurus is an extinct genus of reptile from the early Permian of southern Africa and South America. It is a member of the family Mesosauridae and the order Mesosauria. Mesosaurus was long thought to have been one of the first marine reptiles, although new data suggests that at least those of Uruguay inhabited a Herpesine water body rather than a typical marine environment. The second one is Cynogatus. Cynogatus is an extinct genus of large-bodied cynodontian therapsids that live in the Middle Triassic. It is known from a single species. It was a heavily built animal and measured around 1.2 meters in snout-to-vent body length. It had a particularly large head, up to 40 centimeters in length, with wide jaws and sharp teeth. The third is the Glossopteris. Glossopteris is the largest and best-known genus of the extinct Permian order of seed worms known as Glossopteridae. The genus Glossopteris refers only to leaves, within a framework of form genera used in paleobotany. Species of Glossopteris were the dominant trees of the middle to high latitude lowland vegetation across the supercontinent Gondwana during the Permian period. Glossopteris fossils were critical in recognizing former connections between the various fragments of Gondwana. And lastly, the Lestrosaurus. Lestrosaurus is an extinct genus of herbivorous dicynodont therapsids from the late Permian and early Triassic epochs, around 250 million years ago. It lived in Antarctica, India, China, Mongolia, European Russia, and South Africa. 4 to 6 species are currently recognized, although from the 1930s to 1970s, the number of species was thought to be much higher.
And I'll be discussing the third evidence of Wigner's theory, which is rock and mountain correlation. Rock and mountain correlation. For example, if you take the mountain ranges of North America and Europe, they align perfectly well. Mountains are typically formed when two opposite land masses collide with each other, triggering the rock found at the point of collision to fold or bulge upwards. Okay, so the explanation of rock and mountain correlation is when two opposite tectonic plates collide, the land goes upward. That can make mountains and rock formation. The perfect formation of mountains are seen nowadays. That's why it is one of 4 evidence of Wigner's theory.
So now I discuss all about paleoclimate data. Among other things, Wigner studied paleoclimate indicators and sedimentary strata. He studied the geologic literatures and recognized that occurs Paleozoic, Carboniferous, and Permian. Strata in the northwestern Europe, strata contented extensive coals that could only have formed in a hot, wet climate like the present of equatorial region. In rocks of the same age, equatorial Africa, he noticed were glacial litimate. This indicated to the beginner that the continent must have moved Europe from near the equator, Africa from the polar region into the equatorial region.
So, to understand our world's changing climate, it is imperative that we understand how climates of the past varied. This collection brings together a series of papers published at the scientific data that describe and share valuable data on past climates. Climate data, the data were obtained from a variety of sources, including historical records that can inform us the recent past, and biological or fossil proxies that allows us to learn about climates that existed long before man walked the earth. They have been organized below into two sections according to the level data processing.
The continental drift hypothesis refers to the theory where at one point in a time, all of the continents were joined together in one large landmass prior to splitting apart and drifting into the current positions, known as the various continents in the world today. The continental drift theory states the movement of tectonic plates which drift apart from the land which sits on top is the cause for this shift. When the land spread apart, it formed individual smaller land masses known as continents. Continental drifts are caused by the spreading of the seafloor when tectonic plates, also known as massive slabs of rocks, move. This causes the land masses or continents to drift and move apart from one another.
Examples include the Appalachian Mountains of eastern North America, linked with the Scottish Highlands, the familiar rock strata of the Karoo system of South Africa, matched correctly with the Santa Catarina system in Brazil, and the Brazilian Ghana mountain ranges agreeing over the Atlantic Ocean.